Hello. This lecture is the general change of variable. We already did a change in variable when we did polar coordinates, and then we did cylindrical coordinate systems and spherical coordinate systems. So now we're going to talk about the same ideas in general. So let's begin, and this works for the plane or space. So I'm going to keep it simple, I'm just going to draw a plane here in the XY coordinate system, and say we have some kind of region. We'll call that R. And let's say we have a function in X and Y. And the goal is to integrate this function. So it's be a double integral over the region. And the area here, we'll call it dA for the differential of area. Well, dA is, by definition, dx dy. So here's the problem. And let's assume that this is a difficult problem to do as stated. So what we're going to do is change the variable, do some kind of transformation. So let's do that in red. So we're going to go from the XY coordinate system to say, well, let's first use the example of polar coordinates. So let's transform to the R theta coordinate system as a particular example. Then we'll do the general theorem. So when you do that for polar coordinates, the equations are x is r cosine theta and y is r sine theta. So under this change of variable, which is just a phrase for a transformation, under this transformation, the region, say, turns into something simpler. So I'll just draw that as the example. So here's the new region. We'll call it R prime. And dA turns into a new kind of dA. So we'll just call it dA prime. And our variables are R and theta because this is the equations that determine that transformation. So, what is this equal to? Well, we're still going to have the double integral, but now it's not over R, it's over R prime. Hopefully that's going to be simpler, so we can set up bounds that are simpler. The function's the same except that we're turning x into this and y into this. So now it's going to be a function of not x comma y, but r comma theta. Alright? And we saw in the previous lecture that dx dy turns into r dr d theta. Alright, so dr d theta correspond to a change in r and a change in theta. And this is the scaling factor that makes this work, makes this an equality. So the idea is we take a difficult problem of integration, difficult or perhaps impossible to do, and we transform it into something that we can do, hopefully. And that transformation is this. So this factor here is a scaling factor. It kind of takes dA and stretches it into dA prime. And it's called R, this value here is called the absolute value of the Jacobian. Alright? So what we're going to do next is the same problem, but not polar coordinates. We're going to do it in general. And we're going to figure out what that Jacobian is. And the idea is, when you have a difficult problem, changing to polar or cylindrical or spherical just may not work at all. And we may have to come up with our own transformation. And if we can come up with our own transformation that makes a hard problem easier, in order to evaluate it, we need to determine what that Jacobian value is, that stretching factor value. So, we're trying to figure out double integral r prime. Instead of xy, let's transform it in general to s and t. Alright, so the new variables are going to be s and t instead of r and theta. So of course we're going to have ds, dt, and then we're going to have this Jacobian thing, and it's the absolute value of the Jacobian. And that's because when we calculate a Jacobian, it's really the cross product of two vectors, and it's not this. Let me rephrase that. It's the determinant of a matrix of partials, and it's not necessarily positive, but we know areas scale in the positive sense, so we have to write the absolute value of that Jacobian. All right. So R turns into, like before. The picture's the same. dA prime. And all we have to do is come up with that transformation. So let's assume in general, the transformation is x is equal to some function, and we'll call the function x, in s and t. Okay, so this is the variable x, and this is a function x in s and t. It might be x equals s plus 2t or something like that. And y is some function in s and t. All right, and then we're trying to figure out what this j is. Okay, well j is equal to, here's what it's equal to symbolically. We write the partial of the variables on the left-hand side, the from, remember this is the transformation, from xy plane to the st plane. So it's the partial, we write x comma y, and we put a line here. It's not really division, but it's the way it's written. Partial, and the variables there are s and t. Okay, this is just symbolic. What it's equal to is the determinant of a 2 by 2 matrix. Now it's 2 by 2 because we're working in the plane. This theory also works in space. So in space it would be a 3 by 3 matrix. But here in the plane we're going to work in 2 by 2 matrix. And the way you write it is you take x and repeat it. And you take the second variable here, y, repeat it. And then the new variables, s and t, we're going to take the partial of x with respect to s, and then partial of x with respect to t, partial of y with respect to s, partial of y with respect to t. So now we have a 2 by 2 matrix, and the formula is to take the determinant. Alright. Okay, this is the determinant symbol. It's the same as the absolute value symbol, but they do different things. So this is the determinant of a 2 by 2 matrix. And by definition, it's this times this, xs minus yt, nope, sorry, xs times yt minus ys times xt. And there we have it. So all we have to do is take the absolute value of the Jacobian, and plug it into that formula that was on the board a couple of minutes ago. And we're done. So, let's do an example. Let's stay in the plane. So we'll work with, actually this should be blue. And we'll work with an ellipse, and this value will be A, and this value would be B. So here's our region, and here's our dx dy, or dA, if you like. So what's the equation for the ellipse? Well, it's, if we recall, it's x squared over a squared plus y squared over b squared is equal to 1. Okay. And let's say we want to figure out what the area is. Well, the area is just the double integral of dA, and dA is just dx dy. Alright. The problem is the bounds are complicated. So x goes from, well, you have to solve for x, and it's kind of messy. It's hard to do, if not, I won't say impossible, it's just difficult to do this double integral over the region R. So what works is, well, let's say what doesn't work. Polar coordinates won't do anything for this. Okay, and cylindrical and spherical don't apply because this is in the plane. So we have to invent a transformation that will work. Well, this one's really simple. I think you can see if we just let x over a be equal to s and y over b is equal to t, then this complicated equation turns into, I'll put it down here, s squared plus t squared is equal to 1. Alright? And in the st space, or plane actually, this ellipse turns into the unit circle. So this region turns into a nicer region. And dA turns into a different kind of dA. We'll call it dA prime. Now, our theorem says the double integral of a function, well, the function is just 1. So it's sort of like a trivial function. It doesn't really do anything in this particular example. But on the right-hand side, we have a r prime, and we have ds dt, and all we need is that stretching factor, that absolute value of the Jacobian. Alright? So let's calculate it, and we'll be done. So I'm going to take this out. And if you remember the definition of Jacobian, we had to write x in terms of s and t. Well, x is as, and there's no t, just happens to be no t, and y over b. If you solve for y here, y is equal to bt. So the Jacobian is equal to, if you recall, it's the partial of x with respect to the first variable s. Well, that partial is just a. And then the partial of x with respect to the other variable, t, well, that's just 0. The partial of this with respect to s is 0. Partial of this with respect to t is b. And we're going to take the determinant. Okay, the determinant of a 2 by 2 matrix is this times this minus this times this. Well, that's just AB. Okay, so our formula is the double integral over r prime. Well, I erased it. Well, remember what it was. It was just the unit circle. That's r prime. The Jacobian, the absolute value of the Jacobian, well, this is the Jacobian. A and B are necessarily positive, so this is already positive. So the absolute value of AB is just AB ds dt. And this is equal to, this is a constant, AB. And what's the double integral over the unit circle of ds dt? What's the area of the unit circle? Pi r squared, but r is 1, so it's just pi. So this double integral is just pi. And so that's the answer. This is the area of the original problem, the area of the ellipse. Okay. Now, if we were doing spherical coordinate systems, I'll just quickly go over that without actually doing it. You remember in spherical glue, the formula to do the transformation where x equals rho sine phi cosine theta. You know, it's a lot like r cosine theta. Then we have y is rho sine phi sine theta. And z was rho cosine phi. So this was our transformation. So the Jacobian is, this is now in space, so it's R3. So we have the partial of x, y, z divided by the new variables are not s and t, it's rho phi theta. And if you recall, the Jacobian was the determinant of the 3 by 3 matrix this time, and it was, you just write x, 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 y, 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 z, 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 and then you take the partials with respect to rho phi theta, and then the same thing, rho phi theta, rho phi theta, the determinant. And if you remember how to take the determinant, I'll assume you know how to do that because I'll assume you did cross products of vectors. It's this times this minus this times this, and so forth. Minus this times this minus this times this, and so forth. It's a big long formula. But anyway, I won't write it out. This is how you determine it. How you determine it. It's the determinant of the 3 by 3 matrix. So all I have to do is, fill in these values. So what's the partial of x with respect to rho? Well, that's sine phi cosine theta. You fill in all these values, you do the determinant, and you do a whole bunch of trigonometry involving sine squares plus cosine squares equals 1. And about 30 minutes later, the answer is going to be rho squared sine phi. And if you remember from the previous lecture, for spherical dx dy dz was equal to rho squared sine phi d rho d phi d theta. Okay, so that's general change of variable using Jacobian. One of the more important things in multivariable calculus. I think one of the reasons is important. Well, engineers use this all the time, and the easy part is the calculus. The hard part is figuring out what that transformation, those transformation equations are. So, that's what makes, that's why engineers get the big bucks. End of lecture. Have a nice day.